Hey, hello everyone. My name is Surena Hozoori. Let me thank the organizers again for the invitation to speak at Nearly Carbon Neutral Geometric Topology Conference. And I want to talk a little bit about contact and symplectic geometric characterization of Anosov flows in dimension 3 and discuss some consequences. So I have discussed the necessary background for understanding the main result in a separate video in which I talk about like some basic notions in Anosov dynamics as well as contact and symplectic topology. So if there's any notion that you're not comfortable with, I would recommend taking a look at that video. So for this talk, which is the second part of my talk, I'm going directly to the main result. So during this talk, assume that M is an oriented connected closed free manifold. And as I mentioned, my goal is to give a contact and symplectic geometric characterization of Anosov flows in dimension 3, and then use this characterization to basically deliver tools from contact and symplectic topology in this, to the study of questions in Anosov dynamics. So let phi be a flow on this free manifold M generated by some C1 vector field X. This flow is Anosov if and only if, so notice that this is an if and only if statement. First of all, the direction of the flow is in the intersection of a pair of positive and negative contact structures, C plus and C minus, which are transverse. So remember that's equivalent to the flow, for the flow to be projectively Anosov, which is a more general notion than being Anosov. And then these are like the extra conditions which make this projectively Anosov flow Anosov. And there exist contact forms alpha plus and alpha minus for C plus and C minus, such that the two linear interpolations, 1 minus T alpha minus plus 1 plus T alpha plus, and minus 1 minus T alpha minus plus 1 plus T alpha plus are Liouville forms on M cross interval. So let's try to read this a little bit more carefully again. So notice that M cross interval, so M is a 3 manifold, so M cross interval is a 4 manifold. And I'm using this parametrization T for this interval, let's say from -1 to 1. Since alpha minus and alpha plus, they're like just one forms on the boundary of this 4 manifold. These interpolations, they can be seen as a one form on this 4 manifold M cross interval. So basically, if you look at the boundary of M cross interval, you can think of one of the boundary components as M and C plus, and the other boundary component as minus M and C minus. So notice that C minus is a negative contact structure on M, which makes it a positive contact structure on minus M, by which I mean M with reverse orientation, right? So if I can choose alpha plus and alpha minus on these two boundary components in a way that this linear interpolation, extension basically inside this 4 manifold is a Liouville form, then I can, use that to get anosovity of the flow. So notice that that means that both these alpha minus alpha plus as well as minus alpha minus and alpha plus in this situation, they're giving exact symplectic feelings for this disconnected manifold MC plus union minus MC minus. And I want this exact symplectic feeling, I want this exact symplectic structure to be given by this linear interpolation of these two one forms that I have on the boundary components. For one, I need this to be true both for alpha minus alpha plus as well as minus alpha minus and alpha plus. Okay. To talk a little bit about the proof, the main elements are, first of all, I will introduce some geometric quantities, which I'm going to call growth rates. And these are going to help me actually calculate, do some calculations and basically prove anosovity and show that that anosovity is equivalent to that symplectic condition that I have. However, if in order to make things work, I will need some careful geometric approximations to address the lack of regularity in the setting. So remember that even when the flow is C infinity, The setting that I'm dealing with, the splitting and the foliations, the stable and unstable foliations, they're all in general just C0. So in order to go from a C0 setting given by the definition of anosovity to a C1 world of contact geometry, so remember in contact geometry, all these one forms are going to be C1, right? To go from this C0 setting to this C1 setting, basically I will need some careful approximations to make things work. And that's really like the technical part of the proof. To talk a little bit about the growth rates, so let X, the first condition was X being projectively Anosov, which was the same thing as saying that X is in the intersection of a pair of positive and negative contact structure. So remember that that means that I can have a like invariant and continuous splitting of this normal bundle of the direction of the flow, such that I have relative growth in the EU direction. And now my goal is to measure like the infinitesimal growth and decay in these two directions and try to understand the conditions that make this relative growth and absolute growth in the unstable direction and absolute decay in the stable direction. So let ES and EU, like ES tilde and EU tilde, be these unit vectors in these two directions. And remember that I can always assume that the metric, the norm that I'm using in the definition is differentiable in the direction of the flow. And I can very naturally define these growth rates, RS and RU, in the following way. So I define RS as the derivative of a logarithm of the magnitude of the push forward of like this ES. So remember that the flow phi induces a flow on this normal bundle, which is called the Poincare linear flow. And I can look at the push forward of this vector, or like I can look at the action of this Poincare linear flow on this vector and measure like how fast the length of this push forward is growing. I do it once for the stable direction. I call that RS, the growth rate of the stable direction. And I do it again for the unstable direction. And I call that the growth rate of the unstable direction. But now how can I use these two like very natural quantities to reformulate the condition of anosovity? So for the first kind of easy proposition is that for any metric which I can use in the definition of a projectively Anosov flow, I will have RU minus RS as a positive number. So I can use that metric to measure these growth rates. And I can easily see that in that case, RU minus RS is always positive, and it's kind of simple to see that because this is like showing the relative growth in the unstable direction versus stable direction. This is just saying that I will always have more growth in the unstable direction versus the stable direction, which is actually the definition of being projectively Anosov. And it's not surprising that being Anosov then would be equivalent to finding a metric for which these growth rates satisfy RU being positive and RS being negative, which means that I have absolute growth in the unstable direction and absolute decay in the stable direction. So this shouldn't be surprising, right? So now, if we want to kind of like try to like attempt like the proof, so the flow lying in the intersection of a positive and negative contact structures means that it's projectively Anosov. That in a very, very ideal world, which is basically never happens, Gis showed that not that never happens, but it only happened in the very special case where the flow is either a suspension flow or the geodesic flow of a hyperbolic surface. But imagine for simplicity that everything is smooth. The splitting, the Anosov splitting is smooth, the metric is smooth, everything is smooth. Then we can use this RS and RU to carry such a computation. So we can, for an appropriate choice of alpha minus and alpha plus, we can show that d alpha which d alpha, so I use basically RS and RU, the information from the metric, to define these one forms alpha plus and alpha minus. And if alpha is the interpolation of alpha minus and alpha plus, the interpolation inside my 4 manifold, it will be easy to compute that d alpha of h d alpha, let's say evaluated in the middle of this interpolation, is going to be RU times some volume form. And similarly, if I carry the same computation for minus alpha minus and alpha plus, and then look at their linear interpolation, alpha tilde, inside my 4 manifold, then I can measure the alpha tilde with the alpha tilde as, let's say, in the middle of that interpolation, and see that as equal to minus RS times some appropriate volume form. And that's clear that these two, d alpha and d alpha tilde being symplectic, that's equivalent to RU being positive and RS being negative, because we get the closeness automatically when the two form is exact, right? So that is not surprising that you will get the anosovity being equivalent to like these two one forms being Liouville forms. And here again you see a picture which should tell you like why this is working. So these two linear interpolations, one of them will be passing through the unstable foliation, the other one will be passing through the stable foliation. And if you check the symplectic condition while you're passing the unstable direction, you will see that the previous computation actually shows that that's equivalent to having absolute decay in the stable direction. And if you look at the interpolation, the other interpolation which passes through the stable foliation, if you check the symplectic condition while you're passing the stable foliation, you can see that that would be equivalent to the absolute growth in the unstable direction. That is not really a hard computation, but as I mentioned, the main difficulty is to show that everything works in a C0 setting, which is the setting that we're dealing with. All this splitting, and they're going to be the splittings of like these foliations, they're all going to be C0. So you need to, do approximations in a way that respects this, the growth rates in some sense. It respects the the computation that you had for growth rates is not like changed a lot to violate the anosovity. Okay. So in the remaining talk, in the remaining time, I'm going to say a few words about some consequences of this main theorem. There are three categories that I'm going to talk about a little bit. So the first one is about contact and symplectic topology of Anosov flows. So remember that the content of this theorem is that like before this theorem, basically Anosov flows could be seen as some extra dynamical condition on a projectively Anosov flow. But thanks to this theorem, I can look at Anosov flows as some sort of extra contact and symplectic geometric condition on a bicontact structure. So remember that a bicontact structure was a contact geometric equivalent to a projectively Anosov flow. Now I have like this contact and symplectic enrichment of a bicontact structure, which makes it equivalent to an Anosov flow. And it's very natural to now try to understand these Anosov flows through this contact and symplectic topology. We can, in particular, attribute any contact topological property of this disconnected contact manifold, MC plus and union minus MC minus, to a projectively Anosov flow. And by these contact topological properties, I mean tightness, symplectic, and any kind of like symplectic fillability. So here I'm not going to define things precisely, but you can guess. When I say tight projectively Anosov flows, that's when both of these two contact structures are tight. When I have, similarly, I can define various notions of symplectic fillability in terms of the symplectic fillability of this disconnected contact manifold. And that gives me a hierarchy which is similar to the hierarchy that I have in contact topology in terms of tightness and fillability. On one hand, I have a very general class of projectively Anosov flows, which is, I know is abundant. There are lots of projectively, and there are actually infinitely many projectively Anosov flows even on the sphere. On the other hand, I have the very rigid case of an Anosov flow, which is rare and harder to find and classify. And it's a natural line of questioning to ask, okay, what does each bi-contact topological layer imply about the dynamics of that class of projectively Anosov flows, and which, or in other words, just take your favorite property of like Anosov flows and try to understand like which contact topological layer is responsible for that property. Along these lines, at Nair and Grice, they show that there are no tight projectively Anosov flows on the sphere, generalizing the non-existent of Anosov flows on the sphere. And remember that, as I mentioned before, we have examples of tight projectively Anosov flows on the torus and Niels manifolds, as well as non-Anosov examples of like tight ones on hyperbolic manifolds as well. And Asaoka, Dufresne, and Noda, they show that there exists an over-twisted projectively Anosov flow, which means that when both of the contact structures are over-twisted, when there is no algebraic obstruction. I find this theorem quite interesting because it should remind you of the Eliashberg theorem, which gives you a classification of over-twisted structures purely in terms of algebraic topology. So this is in some sense similar. It is not a complete classification. It at least tells you that there exists one when there is no algebraic abstraction, and it's a natural question to try to give a complete classification, and it's believable that maybe that classification is purely in terms of algebraic topology. Also along these lines, Hyun Kim Min and I, we can prove that when the both contact structures are universally tight, which means that even the lift of these contact structures to the universal cover is also are also tight, then the flow, the projectively Anosov flow, does not have any contractible orbit, which generalizes the same condition for Anosov flows. And I should mention that in terms of like this hierarchy that I showed you, again, similar to contact topology, you can ask about the properness of these inclusions. I can also give you examples on torus. It's actually very easy to build examples on torus, which are actually weakly feelable projectively Anosov flows, but are not strongly feelable. Another line of questioning that I'm very interested in is about like the periodic orbit of Anosov flows, and try to understand contact and trying to use contact and symplectic topology in order to understand questions about these periodic orbits. Like any kind of class of dynamics, it's always interesting to understand periodic orbits. I should mention that if you take a periodic orbit of any projectively Anosov flow, by construction, that's tangent to both of the contact structures, C minus and C plus, which means that it's Legendrian, which is the definition of being Legendrian is just being tangent to these contact structures. And also, when the flow is furthermore Anosov, if you look at basically this periodic orbit times interval, and if you look at this inside the these four manifolds that I constructed, you can easily say that these are actually exact Lagrangian annuli. They are Lagrangian. Being Lagrangian annuli means that the restriction of the symplectic structure on this annuli is going to vanish. And actually, they are actually exact Lagrangian annuli. And the point is that these are very well studied and well-known objects in contact and symplectic topology, and can be now transferred tools to, for instance, understand the knot theory of like these periodic orbits. As far as I know, like there's not much known about the knot theory of like these periodic orbits of an Anosov flow. So can we use like Legendrian knot theory to understand like this knot theory of like these orbits, or like any other kind of question? One conjecture that I think it's motivating along these lines is to show that homotopic periodic orbits of Anosov flows are actually isotopic as knots. And maybe we can use what we know in contact and symplectic topology to answer this question. I should mention that this is proven in the R-covered case by Barthelemy and Fenley. When I say R-covered, if an Anosov flow is called R-covered when the lift of both the stable and unstable foliations to the universal cover are just the product foliations or the trivial foliations of R3. And this is in some sense a simplifying condition on the universal cover, but as you know, we only have a unique tight contact structure on, on R3, like one unique positive contact structure and one unique negative one. So it's not very surprising if you see that we don't need this like simplifying condition in the universal cover if we attack this conjecture from the viewpoint of contact and symplectic topology. And the last direction that I think is interesting to go from this, the main theorem is a little bit more of dynamical and geometric nature. So, and that is about the local theory of like these, this flow. So basically, because we don't have equivalent theorems of like Darboux theorem, Gray theorem in the bicontact setting, the local theory of these bicontact structures are actually way more subtle, and there are lots of things that we don't know about. And in order to motivate understanding these local structures, this local theory is a very important problem in Anosov dynamics, which is to basically classify Anosov flows up to orbit equivalence. I mean, I'm going to discuss why this is related to this by local theory of bicontact structures. So remember that two flows are orbit equivalent if there exists a homeomorphism sending the orbits of one to the other, and that turns out to be the natural equivalence class for a lot of problems in Anosov dynamics. And in particular, Anosov also showed that Anosov flows are structurally stable in the sense that if you perturb an Anosov flow, not only stays Anosov, but it will be actually equivalent, orbit equivalent to the original Anosov flow which you started with. Now, in the light of the main theorem of this talk, we can basically split this problem of classifying Anosov flows up to orbit equivalence into two problems. One of them is a contact topological problem, which is to basically doing a contact topological classification of bicontact structures that will give you a classification up to bicontact homotopy of these structures, which is in nature a contact topological problem. We have lots of tools in contact topology for understanding and classifying contact structures. Probably we can use them also for bicontact structures in many cases. And the second part of the problem will be to understand the bifurcations of projectively Anosov flows under homotopy, which is more of a dynamical problem. So if I understand the first problem, that's like understanding these homotopy classes of projectively Anosov flows. And then I can basically ask how many islands of Anosov flows can I have in one homotopy class of projectively Anosov flow? Maybe I have a unique island of Anosov flows. Maybe I have a couple of islands, but all of them are orbit equivalent, right? And ideally, that would be amazing to show that if two Anosov flows, which are homotopic through projectively Anosov flows, those two are actually orbit equivalent. In other words, there's a unique orbit equivalence class of Anosov flows inside the homotopy class of projectively Anosov flows. Again, notice that these homotopy classes ideally can be understood through contact topology without much use of dynamical systems. And it's a general open problem in Anosov dynamics. Is to ask, like, are there manifolds admitting infinitely many distinct Anosov flows? As far as I know, we don't have any example yet. And at least I think in the atoroidal case, we have good reasons to believe that that might not possible. In other words, maybe we can show in the hyperbolic case, we have finitely many at most Anosov flows on any manifold. Remember that a related fact is that we have, I think it's a result of Colin and Honda, that we have only finitely many tight contact structures on hyperbolic manifolds. Maybe we can use this finiteness of tight contact structures to help this showing that we have at most we have finitely many on hyperbolic manifolds, and answer this problem at least for hyperbolic case or a toroidal case. But this is generally an open problem, and I'm going to end my talk with this open problem. Thank you for listening.